Welcome. This is the fifth video in this series in which we study the gaps between primes by studying the gaps in the cycles of gaps across the stages of Eratosthenes' sieve. In this video, we're going to focus on surviving the sieve. That is, what does it take for a gap in the cycles of gaps to survive further fusions and be confirmed as a gap between primes? Here's where we are. We now have exact models, these functions W, for the relative populations of the gaps in the cycle of gaps. So the raw population for a gap in that cycle is the relative population times the super-exponential growth. We know that all the raw populations grow super-exponentially by that factor of p minus 2, so we take that factor out and study the coefficient on that super-exponential growth. And that gives us those curves we had looked at in previous talks. So in the cycle of gaps, the next composite number, once we have run Eratosthenes' sieve through a prime, say pk, the next composite number will be the next prime, pk plus 1, squared. So all of the gaps from the new prime up to the new prime squared will be confirmed as gaps between primes as the sieve continues. Pk plus 1 squared will be the location of the first fusion. We call that mark the horizon of survival for the cycle of gaps. Let's look at an example of the horizon of survival and how it advances. So here we have the front of the cycle of gaps for 13 primordial. The cycle itself has 30,000 gaps, so this is the first few hundred gaps shown here in that cycle. Up top we have the front of the cycle itself. And then under the recursion that produces the cycle for 17 primordial, the first fusion will take place at 17 squared, and there will be a few other fusions along the way there. Then it advances out to 19 when we apply that recursion. The recursion for 23 advances it further, with 23 squared being the first fusion in that stage. There's 29 and 31, 37, and we can see the horizon of survival advancing unevenly. Although for 13, the horizon of survival is all the way out to 17 squared, everything up to 13 squared was already confirmed that no more fusions would happen behind that mark. So the interval that is uniquely fixed for survival by the recursion at that stage is this interval of survival from the current prime squared to the next prime squared. So that's our interval of survival. And here we've highlighted those intervals of survival over the examples that we just stepped through. And we'll note that the span of the interval of survival is proportional to that distance between next prime and current prime, that particular gap, pk plus 1 minus pk. And so we see that the spans of the intervals of survival are irregular, but in a predictable way. So here's how we're going to put this to use. That interval of survival may be the best place where the distribution of gaps in the current cycle of gaps is preserved. And that if we go out to that interval of survival and take samples there, that's where we should see that distribution of populations of gaps reflected. Let's try this. Let's go out to the prime, 3,919. That's at system parameter lambda about 0.45. The relative populations at this section should be reflected in the intervals of survival for primes around 3919. So what we do, we're going to tabulate the gaps between primes over 22 intervals of survival from 3,767 squared through 3931 squared. Here's how we set this up. We put that section of those graphs over on the left-hand side as a reference. So there's our reference. We have the section of graphs for those weights around lambda equals 0.45 over on the left. And then we will lay out the primes from here from 3767 up to 3931. And we also note that pk plus 1 minus pk value, those gaps, and we color code those gaps. So all the 2s will be bright red, all the 14s will be yellow, the 10s will be green. And there are the samples. Here are 22 intervals of survival by working in this range of gaps. How do these work? The way to read these graphs is, let's take a look at 2 intervals from 3881 and 3889 up to 3907. So we're going from between the squares of those numbers. So we go out, and in that first column, we're looking at all of the gaps 2 in that interval of survival. That's represented by the pink band there. The accumulation of gaps 2 in that second interval of survival are in that slate blue band. Then we accumulate the 4s. The third column accumulates the 6s in those bands. And then here we are looking at how many 12s, gaps of 12 were in those intervals of survival for those 2 samples. Now we can look at the accumulation of the core sample across these 22 intervals of survival, and we see that there is an alignment with the predicted distribution across the gaps. What this is saying is the samples in the intervals of survival are roughly uniform samples from the total relative populations of gaps in the cycle of gaps at this stage. We see the 6s up top, then coming down, we see the 12s, the 2s and 4s, then 10, 18 is about where it should be, 8, 14, the peak for 24. Notice the peak for 30 is starting to come up above the crowd. We do this to see that parade of peaks for the multiples of 6. They have that prime factor of 3 in them, which is boosting their asymptotic score. We observe this alignment, this uniformity, in 2 different ways. First, the column heights agree with the relative population models to first order. But second, if we look within each column, so if we focus just on that third column, the one for 6s, the tallest column, we note that the bands within that column are proportionate to the gaps on the right. That is, the green band for 10 should be about 5 times the size of that bright red band for 2. The dark blue bands for 6 should be about 3 times the size of a bright red band for 2 within each column. And so this is saying that as we take these samples, there's a low variance in the statistics because we are not seeing wild fluctuations from interval of survival to interval of survival and getting some sort of average behavior. Within each column, from sample to sample, interval of survival to interval of survival, we're seeing this regularity. Let's do another example. Let's go out to the prime 31,063. Here, lambda is about 0.36. We put the section for the graphs over there on the left. And here are the samples from 38 intervals of survival, from 31,013 squared to 31,337 squared. This is over 975,000 gaps between primes. And again, we see the 6s up top, 12s. Notice the 10s and 18s at this point, they should be passing up the 2s, and we see that occurring. There's 8 coming up from below, 14 has advanced, and then 24 and 30 are rising rapidly. Let's make one more sample, the largest sample we've been able to do to date. And this is for the prime, around the prime 2724079, so 2.7 million. Lambda's about 0.25 here. If we look here for a second, what we would expect to see here is that 6, 12, and 18 would be up top, and then 10 will have clearly passed up the 2s and 4s, and 30 and 24 should be crossing the 2s and 4s at this point. 30 should really be accelerating. And now here's the samples. Here we took 14 intervals of survival from the prime squareds to the prime squareds. The color coding for those distances between those primes is over on the right. This is a sample of 31 million gaps between primes. This is the data, gaps between primes. And again, we see pretty good alignment between this sample and what we would expect from the models. There are 6, 12, and 18 up top. 30 is starting to pass up 10 and 24. There are the 2s and 4s, lots of 2s and 4s in this range. We have over 1.25 million twin prime pairs and over 1.25 million gaps of 4. This completes the trunk line of our studies. When we started these videos, we wanted to introduce the cycles of gaps and the recursive construction between them and view that as a discrete dynamic system. We then analyzed that discrete dynamic system and extracted exact models for the relative populations for all gaps up to that bound 2 times P1, taking our initial conditions from the cycle for P0 primordial. And then we wanted to introduce this concept of the intervals of survival and compare those samples of gaps among primes to the distributions across the relative population models. So where is that distribution of relative populations in the cycles of gaps reflected among the gaps between primes? So where do we go from here? We'll take a moment and summarize the evidence that the cycle of gaps provide toward this family of conjectures, the twin prime conjecture, Polignac's conjecture, the Hardy-Littlewood estimate. Then we'll also, as a kind of a special topic, we'll show that the biases and the last digits of consecutive primes made kind of a splash in 2016. They are entirely expected. It would be surprising if they did not see the biases. Not only are they expected, but the cycles of gaps suggest they're transient. And then finally, we will extend the analysis we've done to constellations, that's sequences of gaps. And this will make that connection between this work and the K-tuple conjecture.